The title of this note is linearization, and the outcome is I can find a linearization and use it to approximate value. So what is a linearization? We talked about this when we first talked about tangent lines. All graphs are locally linear. That means when you zoom in very, very, very close, the curve begins to look like a straight line. So the tangent line is a really good approximation of the curve if we're very, very close. Basically, the curve and the tangent line look practically identical if you're zoomed way in. So linearizations are used to approximate values. So linearization is actually a verb to linearize. So what we're doing is we're turning curves into a bunch of really local straight lines because we can calculate equations of straight lines much more easily. So this is actually what your calculator is doing. Your calculator does not actually calculate values. So when you're typing like the sine of 3 pi over 4 into your calculator is not actually calculating that. Instead, what it's doing is it's doing this calculus of becoming a very, very locally linearized curve. So let's look at a formal definition. So we have a picture here. What I hope you can see is that in blue we have the curve, and in red we have the tangent line. And if you're zoomed in very, very close, the curve and the tangent line are practically the same. So if you wanted to find a value on that blue curve, what you could do instead is you could find the tangent line, that red tangent line, and you could find a value on that red tangent line, and you'd be pretty close to the answer on the blue curve. This is what your calculator is doing. It's not actually giving you the answer that's on the blue curve, it's giving you the answer on the red line. It's just zoomed in so far that your answer is so close it doesn't matter when you round it on your calculator. So you have an equation for linearization. This equation to here, before you write this down, I want to just talk about where it's coming from. It's actually coming from the point-slope form of a line. So as a quick refresher, point-slope form is actually coming from your slope formula. And what you can do to get y by itself is you can add y1 to both sides. And you can just stick it in front. And that's really what this equation is. Y equals y1 is the output at A. This value right here, we're calling that x value A. And so the output, the height of that value, is f of A. So y1 is f of A. The slope is the derivative at that point, the slope of the tangent line, and then x minus the x value, which is A. So that's what that equation is coming from. And that's what the text below just writes as x is A, f of A is f of x, and the derivative is f prime. So the slope at that point is f prime. All right, so we're going to use a linearization to approximate the square root of 123. This is how your calculator does it. Your calculator does not know what the square root of 123 is when you type it in. It gives you a decimal approximation. It's not some number that's saved in the memory of your calculator. Your calculator actually does this calculus because it's pretty quick to do. We know, we can kind of approximate it. We know that this value is in between the square root of 121 and the square root of 144. So we know the answer is between 11 and 12. And 123 is much closer to 121 than 144. So our answer is pretty close to 11. We can actually get a decimal answer. So this is a function. The square root of 123 is actually the function, the square root of x. It's right, x. With the x value being 123. So let's come up with the slope of the tangent line by taking the derivative. It'd be a lot easier to write this as an exponent That's x to the 1/2. That's the same exponent. We'll just write that so it's more obvious. Which is the same thing as 1/2 square root of x. So if I want the equation of the tangent line, and I want the tangent line at x equals 123. Because if I think about the curve, the square root of x, if I were to just graph this function here, it's going to look like that because it's parabola on its side. And I really want to know what's the output at 123. And without a calculator, I don't know how to do this. And in fact, your calculator doesn't know the answer either. What your calculator does is, your calculator says, you know what we do know the answer of? We know the answer of the square root of 121. So let's linearize the function at 121. That means we're going to draw the tangent line. And let's figure out what the output of 123 is on that line. And as you can hopefully see from the picture, it's really close to the answer on the green function. So the answer on the blue tangent line is really close to the answer on the green function. So what your calculator gives you is the answer on the blue line and just says, well, you know, it's close enough. So let's do that. We're going to use our linearization, which is really just point slope form. I'm going to write it over here. Just move that. So the output of the square root of 121 is 11. The slope is 1 over the square root of 121. Square root of 121 is 11. And 2 times 11 is 22. And then technically what the linearization does is they add the 11 over here so that we have just y equals. Your textbook puts it in front, you can put it in back, it doesn't matter, order of addition doesn't matter. This is the linearization, so the symbol for this is capital L of x, the linearization of the function. That's the equation of the tangent line. Because 123 is so close to 121, let's figure out what the output of 123 is on the linearization. I'm going to input 123 on the tangent line. That's a 1. So 2 over 22 is the same thing as 1 over 11. 1 divided by 11 is 0.09. Repeating. So the square root of 123 is approximately 11.09 repeating, because that's the point on the tangent line, and we're really close to the curve when we're on the tangent line. Okay, so let's look at another quick example. Let's say we wanted to know what is the sine of, so I just want to change that notation to f of x. What if I wanted to know what is the sine of 3? Okay, I want an approximation. Well, 3 is kind of close to 3.14. Kind of close to pi. So what we're going to do is we're going to linearize the sine function at pi. So if I'm thinking about the sine function, okay, here's pi. I want to know what's the output, try that graph again. Okay, I want to know, here's pi. My calibration's being wonky as usual. I want to know what's the output at 3 a little bit to the left. So what we're going to do is we're going to come up with the locally linear line, and we're going to use it to approximate. Okay, pretend those are all straight lines there. So we want the tangent line. And we want the tangent line at pi, because that's something we can calculate pretty easily. So our original function is sine. So the sine of pi, right, we have y minus the sine of pi, and that's the output, equals the slope, that's the derivative, at pi, all times x minus pi. So the sine of pi, this value right here, I'm going to pi on my unit circles, and the output sine y is 0. Okay, my derivative of sine would be cosine. And I want the derivative at pi. So the cosine of pi, again, there's pi, the cosine is -1. So the slope is -1. And if I don't want those parentheses there, I can distribute that negative sign. So -x plus pi. That's the equation of that red tangent line that's supposedly a straight line. When we're close to pi, that tangent line is really close to the sine curve. So if I want the sine of 3, instead of putting 3 onto the sine curve, I'm going to put 3 onto that tangent line and see what I get. Again, this is called your linearization of x. It's similar to f of x. We say f of x is approximately L of x, and L of x, we're talking about f of 3 is approximately the linearization at 3, which would be -3 plus pi. I think it's right, it's pi minus 3. Okay, pi is 3.14-ish, so the answer is about 0.14. Now I could confirm this. I could go to my calculator, type sine of 3, making sure I'm in radians. And I'm actually doing this on my calculator right now. I'm not going to show you, but I'll talk you through it. If I do sine of 3 on my calculator, I get 0.1411. You see I'm pretty close to my approximation of 0.14. So that's it for these.